Okay, here we have another example uh, on the conservation of momentum. Here we have a slender rod, which is the total weight is 5 kg, and it is mounted or pinned here at point O, and it is initially at rest. And you can see on the left here, there is a bullet being fired at the angle of 30 degrees. Okay, the bullet is coming from here, will and finally will stick together it inside this particular rod. Okay, and the speed of the bullet is 400 meter per second. And on this particular problem, we want to determine the angular velocity of the rod just after the bullet become embedded in it, which means we want to determine the omega of this particular rod right after the bullet is fired towards this part here. Okay, let's see on this particular figure up here. What happened just right before the impact, or during the impact, you can see that the bullet is like this. Okay, then the distance is 0.75 from point O and making an angle of 30 degrees. Okay, MB is given 5 kg and VB is given 400 meter per second. Okay, this one just right before the impact. Okay, then we can see that another part here is when the bullet stick on this particular rod. Okay, what we can see here is the uh, the this is our axis system. Okay, and this is our weight of the rod, and this one is the weight of the bullet. Okay, here is 4 gram. Okay, 4 gram, which mean times 10 to the power of minus 3. Then you multiply by 9.81. Then you will get this value. And for the rod is 5 kg times 9.81. So you get this particular value. Okay. Then on the right hand side here, what happened is you can see that right after the impact, we can see that this particular rod together with the bullet which stick together on this particular rod will have a will swing. Okay, will swing like this. Okay, and then uh, from the conservation of angular momentum, we can see that the summation of angular momentum before the impact and the summation of angular momentum after the impact, 0.1 and 0.2 respectively. Okay, before the impact, what we can see is the MB, which is this part here, we can actually resolve that into 2 parts. Okay, into this component, which MB VB 1 cosine 30 degrees. Okay, here what we have. And then we know that the perpendicular distance is 0.75. So it is here 0.75. That is right before the impact. And then what we will have after the impact, we have the rod, okay, this particular rod, and also the bullet. Okay, for the bullet, it will stick here, right? So MB, VB, okay, at point right after the impact, and then multiply by the, because it stick here 0.75 or here from this point O, okay, and it is for the momentum due to the bullet, and also the momentum of this particular rod which will swing, okay, this one. So MR is the mass of the rod, which is 5 kg, and then VG2 is unknown, okay, VB2 is also unknown, and it is the distance because it is a uniform rod, so we can the total length is 1 meter, so we can say that the center of mass is in the middle, so it is 0.5 meter from point O, okay, like so. And then we also have this IG omega 2, okay. Here is the component that telling us that this particular rod will swing. If you don't have this particular component, which means that this particular rod will not swing. Okay, it probably shift or stay like that. Okay. Okay, moving on. Just plug in all the values except for VB2 and VG2 as well as the omega 2. Here we only have one equation. That is a problem. Okay, we have this unknown, and this unknown. We have three unknowns, and we only have one equation. But no worries, no worries. Okay, because the omega is the same along this particular rod. Okay, for this VG2 is just R G, sorry, R point, I put it GO times omega 2. Okay, and then for VB2 is RBO omega 2, which RGO, we know that it is 0.5, and then RBO, it is 0.75. So if you replace this and this into this equation, okay, after you resolve this part here, we'll come to this. So you can see that you will only have one unknown, which is omega 2, like here as well. So finally, you will have one equation and one unknown, and can solve. And you'll see that omega 2 is equal to 0.623 radian per second. Thank you.